Alkyl or aryl derivatives of ammonia are known as amines. Amines formed by the replacement of one or more hydrogen atoms of an ammonia molecule by alkyl groups are called alkyl amines. And those formed by the replacement of the hydrogen by aryl groups are called aryl amines. Like ammonia, the nitrogen atom of amines is trivalent and carries an unshared pair of electrons. The nitrogen atom in amines is sp3 hybridized. Out of the 4 sp3 hybrid orbitals, 3 overlap with the orbitals of either the hydrogen or the carbon. The 4th sp3 hybrid orbital contains an unshared pair of electrons. Hence, amines possess pyramidal geometry. Due to the presence of an unshared pair of electrons, the CNH or CNC bond angle is less than the normal tetrahedral bond angle of 109.5 degrees. For example, the bond angle in trimethylamine is 108 degrees. Depending upon the number of hydrogen atoms replaced by alkyl or aryl groups in the ammonia molecule, amines are classified into 3 types. They are primary, secondary, and tertiary. The replacement of 1, 2, and 3 hydrogen atoms of ammonia with 1, 2, and 3 alkyl or aryl groups yields primary, secondary, and tertiary amines respectively. Amines are called simple amines when all the alkyl or aryl groups are the same, and mixed amines when they are different. Let us now look at the nomenclature of aliphatic amines. In the common system, an aliphatic amine is named by prefixing the alkyl group to the amine. For example, the compound shown here is named as methylamine by prefixing the methyl group to the amine. In secondary amines, if the 2 alkyl groups are the same, then the prefix di is added before the name of the alkyl group. For example, the given compound is named dimethylamine. In tertiary amines, if the 3 alkyl groups are the same, then the prefix tri is added before the name of the alkyl group. Hence, the given compound is named trimethylamine. In case of mixed amines, the names of the alkyl groups are written in alphabetical order. For example, the given compounds are named as ethyl-methylamine and ethyl-methyl-propylamine respectively. In the IUPAC system, alkyl amines are named alkanamines. The name is derived by the replacement of the E of the alkane by the word amine. For example, CH3NH2 is named methanamine. Secondary amines with the same alkyl groups are named N-alkyl alkanamines. Here, N represents the nitrogen atom and should therefore be capital. For example, this secondary amine with 2 methyl groups is named N-methyl methanamine. If the N atom has 2 alkyl groups with different number of carbon atoms, then the alkyl group with the less number of carbon atoms should be treated as the substituent and prefixed as N-alkyl group. For example, in CH3NHC2H5, the CH3 group is considered substituent and is prefixed as N-methyl. Thus, the name of the compound is N-methyl ethanamine. In tertiary amines, if all the alkyl groups are the same, then two alkyl groups are treated as side chains and one is named alkanamine. Thus, the following tertiary amine is named N-dimethylmethanamine. If all the three alkyl groups in tertiary amines are different, then the alkyl group with the more number of carbon atoms is treated as the principal chain and is named as alkanamine. The remaining two alkyl groups with the less number of carbon atoms are treated as side chains. Alphabetical order should be followed while naming the two alkyl groups. For example, this tertiary amine with three different alkyl groups is named N-ethyl N-methyl propanamine. If an amino group is present in the carbon chain, as shown here, then the numbering of the carbon atoms should be done in such a way that the carbon bearing the amine group gets the lowest number. The name of the compound is written by removing the E from the parent alkane, followed by the number of the carbon bearing the amine group, followed by the suffix amine. Thus, this compound is named pentan-2-amine. Let us try to name the given compound. Here, the longest carbon chain has 5 carbon atoms, and therefore the parent alkane is pentane. Since the nitrogen atom is attached to the second carbon atom, the amine is named pentan-2-amine. The side chains, the methyl and ethyl groups, are prefixed as N-ethyl N-methyl in alphabetical order. Thus, the complete IUPAC name of this compound is N-ethyl N-methyl pentan-2-amine. In this compound, apart from the amine group, there is a double bond in the carbon chain. If a functional group and multiple bonds are present in the carbon chain, then the numbering should be done in such a way that the carbon bearing the amine group gets the lowest number. For example, alkyl amine is named prop-2-ene-1-amine. If the compound has more than one amino group present at different carbon atoms in the chain, then the numbering should be done in such a way that the sum of the locants is the least. Depending on the number of amino groups present, a suitable prefix such as di or tri is attached to the amine. Thus, the name of the compound is pentan-2,3-diamine. Similarly, the given compound with 2 amine groups at 1 and 6 positions is named hexane-1,6-diamine. Now let us see the nomenclature of aryl amines. While naming aryl amines according to the IUPAC system, the suffix E of the arene is replaced by amine. Thus, in the IUPAC system, aniline is named benzenamine. Note that aniline has also been accepted as the IUPAC name. Substituted derivatives of aniline are named by assigning the number 1 to the carbon atom that contains NH2 group. The substituents are listed in alphabetical order. For example, this compound is named 4-bromo-2-ethyl-benzene amine. Now try to name these compounds. In the first compound, since 2 methyl groups are present as side chains on the N atom and the main compound is aniline, the compound can be named N-dimethyl-aniline. In the second structure, an NH2 group is attached to alkyl group and a benzene ring is present as a side chain. Therefore, the compound can be named 2-phenyl-butan-1-amine. In the third structure, an amine group is present on the benzene ring and alkyl groups are present as side chains. Hence, it can be named N-ethyl-N-methyl-aniline. In the fourth structure, as 2 amine groups are present on the 2 adjacent carbon atoms, the compound can be named as ethane-1,2-diamine. The laboratory method for the preparation of amines involves the reduction of nitro compounds. The reduction of nitro compounds can be carried out either by catalytic reduction using hydrogen gas in the presence of finely divided nickel palladium or platinum, or by using active metals such as iron, tin, and zinc in the presence of concentrated hydrochloric acid. In this reaction, the nascent hydrogen produced by the action of active metals with hydrochloric acid reduces the nitro compounds to amines. Note that both aliphatic and aromatic primary amines can be prepared by the reduction of the corresponding nitro compounds. For example, nitroethane on catalytic reduction or reduction in the presence of tin and HCl or iron and HCl gives ethanamine. Similarly, nitrobenzene on catalytic reduction or reduction in the presence of tin and HCl or iron and HCl gives aniline. Reduction with iron scrap and hydrochloric acid is preferred over tin and HCl. This is because the ferrous chloride formed in the reaction between iron and HCl undergoes hydrolysis and releases hydrochloric acid. Thus, only a small amount of hydrochloric acid is required to initiate the reaction. Amines can also be prepared by the ammonolysis of alkyl or benzyl halides. In this method, the carbon-halogen bond in alkyl or benzyl halides is cleaved by the nucleophile ammonia. This process of cleavage of a carbon-halogen bond by ammonia is called ammonolysis. It is also referred to as Hofmann's ammonolysis reaction in the honor of the scientist who worked on it. In this reaction, amines are produced when a mixture of an alcoholic solution of ammonia and alkyl or benzyl halide is heated in a sealed tube at 373 Kelvin. For example, when a mixture of chloroethane and alcoholic solution of ammonia are heated in a sealed tube at 373 Kelvin, a mixture of ethanamine, N-ethylethanamine, N-diethylethanamine, and tetraethyl ammonium chloride salt is produced. This is a nucleophilic substitution reaction where the halogen atom is substituted by the amino group. The primary amine thus obtained acts as a nucleophile and reacts further with more of alkyl halide to form secondary and tertiary amines as well as quaternary ammonium salt. The free amine can be obtained from the ammonium salt on treatment with a strong base, such as sodium hydroxide. Ammonolysis has the disadvantage of yielding a mixture of primary, secondary, and tertiary amines besides a quaternary ammonium salt, which is difficult to separate. However, the actual composition of the reaction mixture depends upon the ratio of alkyl halide and ammonia used. If an excess of alcoholic solution of ammonia is used, then a primary amine is formed as the major product. However, if excess alkyl halide is used, then a quaternary ammonium salt is formed as the major product. Amines can also be prepared by the reduction of nitriles and isonitriles. The reduction of nitriles with lithium aluminium hydride or with hydrogen in the presence of catalysts such as platinum, nickel or palladium yields primary amines. For example, ethane nitrile on reduction with lithium aluminium hydride or catalytic reduction gives ethanamine. This reaction has synthetic importance as it is used to step up the carbon chain. Alkyl nitriles can be easily prepared by the action of alcoholic sodium cyanide or potassium cyanide on alkyl halide. Alkyl nitriles thus formed are reduced to get the primary amines. This is an excellent method for the preparation of primary amines. For example, methyl bromide on treatment with alcoholic sodium or potassium cyanide gives ethane nitrile. This on reduction with hydrogen in the presence of nickel as the catalyst gives ethanamine. The reduction of isonitriles or carbyl amines yields secondary amines. For example, ethyl isocyanide on reduction gives ethyl methyl amine, which is a secondary amine. In this method, we get only secondary amines in which one group is always the methyl group. Another method for the preparation of amines is the reduction of amides. Amides on reduction with lithium aluminium hydride yield amines. For example, ethanamide on reduction with lithium aluminium hydride gives ethanamine. A convenient method for the preparation of aliphatic primary amines is Gabriel's phthalimide synthesis. In this method, phthalimide is treated with ethanolic potassium hydroxide to yield potassium phthalimide. This potassium salt of phthalimide, on heating with a suitable alkyl halide, gives N-substituted phthalimide. The subsequent alkaline hydrolysis of N-substituted phthalimide results in the formation of the corresponding primary amine. For example, phthalimide on treatment with alcoholic potassium hydroxide gives potassium phthalimide. This, on heating with ethyl iodide, gives N-ethyl phthalimide. The alkaline hydrolysis of N-ethyl phthalimide gives ethyl amine and phthalic acid. Let us look at yet another important method for the preparation of amines. Hofmann's bromamide degradation reaction. Hofmann developed a method for preparing primary amines by treating an amide with bromine in an aqueous or alcoholic solution of sodium hydroxide. For example, ethanamide on treatment with bromine in the presence of sodium hydroxide gives methanamine. Note that in this reaction, the resultant amine formed has one carbon atom less than the parent amide. Hence, this reaction is used to step down the carbon chain. Let us look at the mechanism of the reaction. As you can see, the first step involves the halogenation of amide to yield N-haloamide. The second step is the abstraction of hydrogen ion by the hydroxide ion. This results in the development of a negative charge on the nitrogen atom. Step 3 involves the separation of halide ion, resulting in the formation of an intermediate with an electron-deficient nitrogen atom. Step 4 involves the migration of the alkyl group from the carbonyl carbon of the amide to the electron-deficient nitrogen atom. This results in the formation of alkyl isocyanate. The last step is the hydrolysis of alkyne isocyanate to yield a primary amine with one carbon atom less than the parent amide. With the knowledge that we have acquired about the methods for the preparation of amines, let us now carry out some conversions. Benzene to aniline, chloroethane to propanamine. In the conversion of benzene to aniline, the first step involves the nitration of benzene using the nitration mixture to nitrobenzene. The nitrobenzene formed in the first step is reduced to aniline in the presence of iron and concentrated hydrochloric acid or by catalytic reduction. Let's proceed to the conversion of chloroethane to propanamine. Note that this conversion involves the stepping up of the carbon chain. To achieve this, chloroethane is first treated with an ethanolic solution of sodium cyanide to yield propane nitrile. In the next step, propane nitrile is reduced by active metals like tin, iron, or zinc in the presence of concentrated hydrochloric acid or by catalytic hydrogenation to give propanamine. Like ammonia, amines are also basic in nature. Their basic nature is due to the presence of a lone pair of electrons on the nitrogen atom. This lone pair of electrons is donated to the proton of an acid to form a new bond. Amines are weak bases as they combine with water to produce fewer hydroxyl ions per unit volume. For example, an alkanamine combines with water to produce hydroxyl ions as shown in the equation here. By applying the law of mass action to the equation, the base dissociation constant or basicity constant Kb equal to the product of molar concentrations of RNH3+ and OH- divided by RNH2. You get an idea of the relative basic strength of amines from their Kb or pKb values. The larger the value of Kb or smaller the value of pKb, the stronger is the base. By observing the pKb values listed in the table, we can say that aliphatic amines are stronger bases than ammonia. On the other hand, aromatic amines are weaker bases than ammonia. The Kb or pKb values of amines are affected by factors like the inductive effect of the groups present in amines, the ease of solvation of protonated amines, and steric hindrance. Consider the inductive effect of an alkyl group of an alkyl amine. Since it tends to donate electrons, an alkyl group R pushes electrons towards the nitrogen atom and thus makes the lone pair of electrons more available to the proton of the acid. Moreover, the alkyl ammonium ion formed from the amine is stabilized due to the dispersal of positive charge by the plus inductive effect of alkyl groups. Hence, alkyl amines are stronger bases than ammonia. Thus, the basic nature of aliphatic amines increases with an increase in the number of alkyl groups. Therefore, the basicity order of aliphatic amines in its gaseous phase is tertiary amine is greater than secondary amine is greater than primary amine is greater than ammonia. On the other hand, the basicity order of aliphatic amines in its aqueous phase is ammonia is greater than primary amine, is greater than secondary amine, is greater than tertiary amine. This can be illustrated on the basis of the ease of solvation of cation. The positive charge on the nitrogen atom is also stabilized by the effect of solvation in aqueous phase. The smaller the size of the ion, the greater will be the solvation with water molecules and more stabilized will be the ion. Thus, the order of basicity of amines in its aqueous phase is exactly opposite to the order based on inductive effect. Another important factor that affects the order of basicity is steric hindrance. If the size of the alkyl group is small, like the methyl group, then there is no steric hindrance to hydrogen bonding in its aqueous phase. If the size of the alkyl group is larger than the methyl group, then there is steric hindrance to hydrogen bonding in its aqueous phase. As the size of the alkyl group increases, the steric hindrance to hydrogen bonding increases and the basicity decreases. Thus, the relatively basic strength of primary, secondary, and tertiary aliphatic amines is due to the combination of inductive effect, solvation, and steric hindrance. Now let us consider the order of basic strengths of aromatic amines. By observation, the pKb values of aromatic amines are quite high. This can be explained on the basis of the resonance stability of aryl amines and aryl ammonium ions by taking the example of aniline or aryl amine. The NH2 group in aniline or aryl amine is directly attached to an aromatic nucleus. As a result, a lone pair of electrons on the nitrogen atom is in conjugation with the aromatic ring. thus making it less available for protonation. On the other hand, the protonated aniline or anilinium ion obtained by accepting a proton can have fewer resonance structures than aniline. You know that greater the number of resonance structures, greater is the stability. Thus, aniline is more stable than the anilinium ion. Hence, the proton acceptability or basic nature of aniline or other aromatic amines would be less than ammonia. In case of substituted aryl amines, electron-donating groups such as methyl, ethyl, and methoxy increase the basic strength, whereas electron-withdrawing groups like NO2, X, SO3H, COOH decrease the basic strength. Here's a problem for you to try. Arrange the given amines in descending order of their basic strengths. Try to work out the answer yourself before checking the solution. The descending order of basic strengths of the amines and ammonia is dimethylamine is greater than ethylamine is greater than ammonia. This is explained on the basis of plus L effect of the alkyl groups. More is the number of alkyl groups, more will be the plus I effect. Here's another problem. Arrange the given amines in ascending order of their basic strengths. Try to work out the answer yourself before checking the solution. The ascending order of the basic strengths of these amines and ammonia is paratoluidine is greater than aniline is greater than p-nitroaniline. Here, NO2 has a minus I effect and is thus less basic than aniline, while methyl group has a plus I effect and is therefore more basic than aniline. Diazonium salts have the general formula Rn2X, where R is an aryl group. The counter ion X- may be a chloride, bromide, or hydrogen sulfate, or a tetrafluoroborate ion. The diazonium group consists of two nitrogen atoms, triply bonded to each other with an overall +1 charge. Aryl diazonium salts are used as intermediates to synthesize a wide variety of organic compounds. To name diazonium salts, add the word diazonium to the name of the parent hydrocarbon. This is followed by the anion name. Consider the compound shown here. There is a diazonium group plus an ethyl group at position 4 on the benzene ring with the chloride anion. The correct name of this compound is para-ethyl benzene diazonium chloride. Can you name this aryl diazonium salt? Notice that there is a fluorine substituent at position 3 of the ring, or the meta position with the hydrogen sulfate anion. This compound is named metafluorobenzene diazonium hydrogen sulfate. Primary alkyl diazonium ions are not very stable. They decompose easily and tend to be explosive when dry. Aryl diazonium salts are stable only for short times at low temperatures. Resonance structures help to stabilize the ion by delocalizing the positive charge around the aromatic ring. To prepare aryl diazonium salts, aniline is reacted with nitrous acid at 273 to 278 Kelvin. The nitrous acid is generated in situ by the reaction of sodium nitrite with hydrochloric acid. The overall scheme is summarized here. Due to the low stability of the diazonium salt, it must be used immediately after preparation. To prepare benzene diazonium chloride in the lab, a solution of aniline is prepared in hydrochloric acid and placed in a beaker of ice. The sodium nitrite solution is also cooled on the ice. The solution of sodium nitrite is then added very slowly to the solution of aniline in hydrochloric acid, keeping the temperature below 5 degrees Celsius at all times. If you use a different acid, you will get a different anion for the salt. Benzene diazonium chloride is a colorless, crystalline solid. It dissolves readily in water It is stable in cold water but reacts with warm water. Benzene diazonium fluoroborate is insoluble in water. It is stable at room temperature. The reactions of aryl diazonium salts can be sorted into two classes. Many reactions of benzene diazonium salts involve the displacement of the diazonium group, as nitrogen is an excellent leaving group. Aryl diazonium ions can also undergo coupling reactions, using the nitrogen atoms of the diazonium group to link to another aromatic ring. We first consider the reactions that involve the displacement of the diazonium group. The first group of reactions that we will discuss are known as the Sandmeyer reactions. In these reactions, the diazonium group is replaced by a chloride, bromide, or cyanide ion in the presence of copper-1 ions. Nitrogen molecules are released as a byproduct of the Sandmeyer reactions. Here is a problem for you to solve. Predict the major organic product of this reaction. The first step of the process converts 2-aminotoluene into the corresponding aryl diazonium salt. You should recognize the second step of the process as a Sandmeyer reaction. Under these conditions, the diazonium group will be replaced by a nitrile group. In the Gattermann reactions, the diazonium group is replaced by a chlorine or bromine group. To carry out these transformations, the diazonium salt solution is treated with the appropriate halo acid in the presence of copper powder. In general, yields for the Gattermann reactions are lower than for the analogous Sandmeyer reactions. Try to solve this problem on your own before checking the answer. Write equations showing the synthesis of this compound from an appropriate aniline derivative using the Gattermann reaction. With these types of problems, working backwards can be a very effective strategy. We need a bromine atom at position 4 on the aromatic ring. So we can carry out a Gattermann reaction using a diazonium group in the correct location. We can make the diazonium salt from the appropriate aniline derivative. Let's put it all together, working forwards from the aniline derivative that we need. We can convert the aniline derivative into a diazonium salt by treating it with nitrous acid. Subsequently, we can treat the diazonium salt solution with hydrobromic acid in the presence of copper powder to form the desired product. The diazonium group can be replaced by iodine ions if the diazonium salt solution is treated with potassium iodide. This reaction forms iodobenzene as the primary organic product. Try to answer this question on your own before proceeding. Draw the major organic product of this reaction. You should recognize the steps involved. Step 1 produces an aryl diazonium ion. In step 2, treatment with potassium iodide replaces the diazonium ion with iodine. The Shemin reaction is a method for making aryl fluorides. In the first step, a primary aryl diazonium salt is treated with fluoroboric acid to make an aryl diazonium fluoroborate, which precipitates. Next, the dry diazonium fluoroborate is heated until it decomposes, releasing an aryl fluoride. Can you give the structure of the expected product for this reaction? You should recognize this as the Shemin reaction. The amine group will be transformed into diazonium group and ultimately be replaced by fluorine. Reductive deamination of primary aryl amines replaces the amino substituent by hydrogen using a diazonium salt as an intermediate. When the diazonium salt is treated with a mild reducing agent such as hypophosphorus acid, sometimes known as phosphenic acid, the diazonium ion is reduced to an arene. Alternatively, this can be carried out using ethanol. Can you complete this reaction? In the first step, the corresponding diazonium salt is prepared. Next, the diazonium group is replaced with a hydrogen atom. Nitration reactions replace the diazonium group by a nitro group. First, prepare diazonium fluoroborate by reacting the aryl diazonium chloride with fluoroboric acid. When the diazonium fluoroborate is heated with aqueous sodium nitrite in the presence of copper, the diazonium group is replaced by a nitro group. Phenols are readily produced from diazonium salts. These reactions cause the diazonium group to be replaced by a hydroxyl group. To carry out these reactions, acidify an aqueous solution of the diazonium salt by adding sulfuric acid at 100 degrees Celsius and heating it. Azocoupling reactions are electrophilic substitution reactions that take place when a diazonium salt is reacted with a phenol or aniline derivative. In these reactions, the diazonium cation acts as an electrophile. while the electron-rich compounds such as phenols and amines act as nucleophiles. The aromatic rings are joined via the nitrogen atoms. The azo products of the coupling reactions have extended conjugation involving both the aromatic rings. As a result, the products are highly colored. They are often used as dyes. For example, para-hydroxyazobenzene is an orange dye. Para-aminoazobenzene is a yellow dye. As we have seen, diazonium salts are very good intermediates for introducing a variety of functional groups onto an aromatic ring. They allow for substitution patterns that cannot be prepared by direct substitution of benzene or substituted benzenes.